Hello and welcome. Today we're going to derive the wave equation two ways. So the first way we're going to do is based on mass springs. And it's going to invoke mass spring systems that you've seen. Invoke knowledge you've learned in 2250, our previous differential equations course. And the second way we're going to do it is the book way, the way you can find in your book. And we're going to compare and contrast them. And essentially they are expressing the exact same thing, but we'll see by looking at both of these, we should get a better picture of what's going on. Anytime you can get more perspectives on a derivation, I think it's helpful. So let's go with way number one based on mass springs. So this is a little refresher. So let's say I let u of t be the position of a mass. I'm going to call that m. I'll just call it mi. Okay? And so we can think of that as being right there. mi. And we're going to just put a little spring on it. And we're going to anchor that to the ground. Okay. So first of all, what we're going to do is assume that gravity is negligible. So what do I mean by assuming gravity? So this is obviously, it could be a very large mass, and this is a big spring or whatever, but the point is the force downward on from gravity is so small relative to the forces involved with the spring that we can just not include them. They would only augment the situation. And that turns out to be a very reasonable thing to assume, as we're going to find out later. We can always sort of subtract off any effect of gravity. Because gravity is, at least on Earth, as long as we're near Earth, is always going to be a constant force down. So we can literally just ignore it. So the forces involved, so we have a spring. So the force of that spring, F, is going to be a function of the position. So here is u. Think of u is equal to 0 as this neutral point right here. And we want to know the motion up and down. So that's going to be u of t, is that motion at time. We'll see that there's a neutral position, and that's going to be equal to negative what we'll call t0 u. All right, so obviously if I bring u up, if I pull the mass upward, we're going to have the spring, of course, is going to want to pull back. It's going to want to pull back to the neutral point. And if I compress the spring down, the force is going to go up. And that's why there's that negative sign associated with the spring force. All right, so that's the first force. And the next force is there's an inertial force. And the inertial force is the standard Newton's second law, that mass I u double prime of t is equal to the inertial force. Okay, so we know that all forces have to balance. So the net force is always, so the force is going to be the mass I times u double prime is equal to negative t0 u. All right, so the solutions to this equation, we can write this down. U double prime is equal to negative t naught over mi equals u, and that has solutions that look like, okay, so obviously what we see here is this constant. We know that the second derivative of a function is proportional to itself, but with a negative sign, it has to be sines and cosines. So u of t is of the form a times cosine square root of T naught over M times T plus B times sine of T naught over Mi, we said those were i's, times T. And of course this is the temporal frequency. So the temporal frequency of the oscillator. So we can also call that a characteristic frequency. All right, and the characteristic frequency depends on this constant here. It's the tension constant. So it's the spring tension. It's the material property of the spring, how springy it is, and it's divided by the mass, which is essentially normalizes that springiness with how big the mass is. Obviously, a slinky and a bowling ball are going to be going to make a very, 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 very small frequency, right? It's going to that'll be a very small T naught and a very, very large M, and that's going to make a very, very small temporal frequency. Likewise, if we have so that means that it's going to be a very, 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 very slow oscillation. Likewise, if we have a very stiff spring and then a very small mass, we're going to have a very large temporal frequency, a very fast oscillation. And so that's the idea. Okay, so what we see there is this notion. But remember here, this is a time derivative. This is du squared dt squared. Okay, so that's our time derivative, and that's how it differs, you see, from the first derivatives we've seen in other PDEs. So now let's talk about a system, a mass spring system. So a mass spring system, now we're gonna do this. So we're gonna have our mass, and that'll be Mi again. But rather than anchoring it to the ground with the spring that's below it, what we're gonna do is gonna put a spring like this, and we're going to attach it to another mass. Call that mass I plus 1, and likewise we'll have another spring on the other side and attach that to a mass I minus 1. And we can keep going like this. Mi plus 2, and so on that way, and again that way. And what we're going to use this as an approximation for a continuum mass where we have something like this. So what we're going to consider now is we have an x direction here. X. So here we'll have xi, that position, and then here we'll have xi plus 1, and here we have xi minus 1. And between here, we'll actually say it's going to be delta x, where this is some, small. Small enough to suit our needs, and that's xi plus 2. And so, of course, we can always write this as xi plus delta x, and this is going to be xi minus delta x, right? So those are the three positions we're going to look at. That'll be xi minus 2. But we're going to really focus on these three positions here, and of course we could do the same for all others, right? All right, and so that's the idea, and we're going to use this as sort of an approximation for little segments of mass on some sort of elastic type string or some sort of continuum medium, right? And so oftentimes what we want to do then is write this mass that's on this is a string. Think of it like a guitar string, or maybe a tightrope for a tightrope walker, or some sort of elastic piece of some sort of elastic one-dimensional thing. And we have these masses there, and we're going to assume we have something like a mass density and that's per x, right? Per distance direction. So then our mass mi will be equal to rho at xi, which will be an approximate. This will be approximate times delta x. So that's per length, per unit length x. All right. So that's our mass I will be right here, rho xi, delta x. And so we can think of it as our delta x then can be right here. And then we have another delta x and another delta x over that way, and so on and so forth as we go forward. All right, so we'd like to write down what's going on here. And so just like before, we have a force, inertial force. And that inertial force is going to be, so the other thing we need to do then is, then we can define that as going to be ui at xi. So ui, or u at xi comma t, is going to be the position of mass I. It's going to be the vertical position of mass I. So we can define that to be delta x, rho of x of I, times, and then we're going to have the second partial of t at x of I comma t. All right, that's the inertial force. And it has to balance what's going on the other side. And what we see here is what we're going to do then is model the strain, the up-down strain then of these masses, is they're connected by these springs. And so this mass here, mi, then has this spring here and that spring there. So there's two forces on this thing. All right, and the first force then, so we can call this, of course, ui plus 1, and that we're going to call ui minus 1. Okay, so there we go. So what we can write down here is that, again, just like before, the force of a spring is going to be negative k times the displacement, or sorry, negative t naught times the displacement. Okay, so times that displacement. So what is that displacement? Well, it's the difference between the two positions here. So it has to do with the relative heights of mass I with mass I plus 1, and also the relative amplitude or height of mass I with I minus 1. So if mass I, now let's look at I plus 1. If mass I plus 1 is higher than mass I, we're going to get a force pulling upward on mass I. So we can consider it to be, it's going to be something involved with T0, right, times this displacement here. All right, so we can think of that as ui plus 1 minus the position of I. Now here's another little tricky business here, is that what happens if I change my approximation? We can see here that that displacement also has a horizontal displacement. So if I shrink my delta x, it should also shrink the displacement. So we need to also think of the position of these masses is per unit element of space that we're going across, right? So that's the first force. So that's the force from mass I plus 1 onto mass I. But then we have this other force. Now this force, you see, if we have the mass going down, if this is below, like it's shown in this picture, this mass is a little higher. Mass I is higher than mass I plus 1. So we can consider this is a force going down, right? So what we need to do then is write this as follows. So we need to talk about that displacement is going in the other direction. So here what we have to do is we'll again write it as, now it's a minus T0, and it's going to be u I minus 1 minus ui. And again, it's per unit length. Okay, there we go. So this looks good. All right, so of course these look a little like derivatives, so I'm going to rewrite that. So this is approximately equal to, and so these are all approximate because we're doing this approximation of a continuum mass by little masses and little springs. And so we can actually rewrite that as t0 is equal to the partial derivative x, and we're going to put that at xi, and we're going to think of that one as the partial derivative of u at xi minus 1. Okay, and that's of course all divided by, or all multiplied by t naught, that spring constant we had. Okay, so now of course we can divide this whole thing by delta x, and it cancels that one there. And what we get is rho at x of I, the partial derivative with respect to time, the second partial derivative with respect to time. And that, of course, looks like a second. So when we divide here by delta x, this looks like a second partial derivative. So we can write that as t naught u delta x, or d times the second partial with respect to x of u. And so, of course, this becomes an equality as delta x goes to 0. Okay, and so that is what we call a model for the wave equation. Or they call this a model for a vibrating string, but they also call this the wave equation. So we'll get to this in a second, what this all means. So that's one model, and that's based on this notion of a vibrating string, and it's based on this thing that we're more familiar with, which is a mass spring system. Okay, so now let's go to another sheet of paper, and now go through a book derivation. And again, it's going to contain a lot of the same elements. It's just a different way of seeing it. So let's now go to that book derivation, and the book derivation has this. So here's our continuum string, and we're going to go from a point x to a point x plus delta x, and the mass on this spring is going to be mass at x is going to be equal to rho times x times delta x, just like before. And we know that our inertial force is going to be, it's going to be delta x times rho of x times the partial of u. So again, u here represents that position, this position right here of the midpoint of this little interval in x. So that will be u. That'll be u of x comma t, and that's going to be the second partial with respect to time, and that's the add inertial force. And now we're going to set it equal to the tension, or the vertical tension. So let's look at some pieces of this. So what we're going to define now is a force vector. I'm going to call it t, and that's going to be t at x plus delta x comma t, and that's the tension vector that this string is experiencing. And there's another tension vector here, t, and that's going to be at x comma t. Okay. Now this has a theta value at x comma t, and this also has a theta value here. Call it x, a theta at x plus delta x comma t. All right. Now we know that we're going to assume something here. I'm going to put a little asterisk. Assume horizontal forces are negligible. And what we mean by that is that we know that the t at x, or so I shouldn't say that they're negligible. I'm going to scratch that. They're not negligible. They're actually quite large, but the forces, they balance. and that is that tx comma t, the horizontal component of this vector, of course, is going to be the cosine of theta x comma t, and that's going to be equal to t at x plus delta x comma t times the cosine of theta x plus delta x comma t. So those force, the horizontal components of the force, that part right there and this part right there, are always going to be equal. So that means if these two forces balance, this mass never moves side to side. So what we interpret from that, only up down forces are relevant. So, of course, in reality, there will be some very, very slight horizontal forces if we're thinking of a vibrating spring. But we'll see that they're so negligible that we're not even going to consider them. They're just tiny. Okay. So only up and down are relevant. So, of course, that's what we call u of x of t is that up and down position. All right, so the up-down forces then are going to be, of course, the vertical component. So the vertical component is going to be, of course, t of x comma t times the sine theta of x comma t of our system. All right, so we can write those down. So this one is pointing up here, and that's the sine. So it's going to be t x x plus delta x comma t times sine theta at x plus delta x comma t. And then it's going to be minus t at x comma t times sine theta x comma t. All right, so that's the balance of those two forces. That net force I'm going to call that net vertical force, and that's this whole thing. That's going to equal the inertial force, the balance of that inertial force. So, and the difference of the combination of those two things, of course, generate motion. All right, so here we go. So now we need another thing. We're going to assume one more thing. We're going to assume that theta is always really small. That the vertical vibrations of this spring under this string under tension is very small, and so that's going to give us the following result. It's going to give us that sine theta is approximately equal to sine theta over cosine of theta, because cosine is basically 1 at this point for very, very small angles, and that's tangent of theta. And that is approximately, and of course that is going to be rise, that's the sine of theta, over run. And so that's approximately going to be the partial of u with respect to x. All right, so that's our very key argument we're making here. All right, and this is something we're going to stick to. And so that means that wherever I see a sine theta, I can replace it with a du dx. All right, and we're going to make one more assumption. We're going to assume that t is a constant. We'll call it t0, in which case we're going to write it as t0 is equal to, and this is going to be the partial of u with respect to x, evaluated at x plus delta x, comma t, minus, and here we're going to put the partial of u with respect to x, evaluated now at x, comma t, put a parenthesis around that. So there you go. So I'm going to get a new sheet of paper and write that down then. So what we have here is delta x times rho of x, the second partial of u with respect to time is equal to t naught, and this is approximately equal, I should say, the partial of u with respect to x at x plus delta x minus the partial u of x at x comma t. And now, of course, we do just like we did before, divide by x, and note that that looks a lot like a second partial derivative with respect to x, and we get the wave equation. So that's a t there. So second derivative with respect to time. So if rho of x is just rho 0, we can it's just a constant. There's a uniform property to our string. We can write it as utt is equal to k uxx, where k is just equal to t naught over rho naught. And we call this typically what we call the wave equation. And notice it looks a little like the heat equation, except for here we have a second derivative in time. In general, when you're diagnosing, if you're looking at a PDE and you see a second derivative in time, you should always think about acceleration. And you should think in terms of inertial forces. Right? That F equals ma. So anytime you're looking at a PDE and you see a second derivative in time, you're immediately thinking in terms of mechanics, in terms of motion of masses. Mass is playing a role in your problem, and you have an F equals ma showing up. And so any kind of second time derivative, it usually has an F equals ma style component to it, and you're talking about mechanics. All right, and that's the difference between the heat equation and the wave equation. Is the heat equation, we were talking about a conservation of energy. We want to know the time dynamics of how energy shifted around inside of some spatial region. Here we're talking about how forces are transmitted through a medium, and so we have to keep track of these inertial forces. So we're saying that the acceleration force, acceleration-based force, is somehow related to these spatial or material forces that were within the medium itself. So that's the idea behind the wave equation. Thanks very much.